Hi guys, welcome back to Math TV with Professor V. This video is for Introductory Statistics Chapter 9, Hypothesis Testing for One Population Mean. And we're going to cover sections 9.1 through 9.4. So first we're going to discuss the steps in hypothesis testing using the traditional method. What is hypothesis testing? Well, it's a decision-making process for evaluating claims that are made about a population. And we use hypothesis testing to answer the question, is the evidence that we have accurate, or you could think of representative of the population, or could this observation be due to sampling error or chance? Okay. So basically we know that when we're trying to collect information about a population, it's often impossible to do so. We can't have a census and pull every member of the population. So we get a sample and we want to know how good of a job does this sample represent the population, or is there too much sampling error for us to make any sort of claims or inferences about the population. So there's a set process for how to test, okay, whether or not these claims can be supported or not. We begin with a statistical hypothesis. So there's a special way that you phrase a hypothesis in statistics, and it's a conjecture about a population parameter, such as the mean, or, which we're going to study later on, a proportion. And this conjecture, just like any conjecture, may or may not be true. A statistical hypothesis has two parts. First part you state is called the null hypothesis, and it's denoted H with a 0 subscript. When you read that out loud, we usually say H naught, okay? In your science classes too, you might see that 0 subscript. It means initial velocity, right? V naught, or initial acceleration. Here, H naught is the null hypothesis. The null hypothesis states that there is no difference between a parameter and a specific value. The alternative hypothesis, which is denoted H and then a 1 for the subscript, also other textbooks will write this as H with a capital A for alternative, or H with a lowercase a. I've seen all of them. So just be on the lookout. They all represent the alternative hypothesis, and it will state that there is a difference between a parameter and a specific value. So this probably makes no sense right now, I get it. Let's just look through some examples, and we're going to practice writing out what the null and alternative hypotheses are for each conjecture, okay? Example 1, the mean age of the students enrolled in evening classes at Harvard University is less than 28 years. So here's the important thing to keep in mind. The null hypothesis will always state that there's no difference. So the null hypothesis will always be written using equality. And then the alternative hypothesis states that there is a difference. So when we write out the alternative hypothesis, it's either going to have a less than, a greater than, a not equal to, a less than or and that's it. And that's it. So those are your three choices. Okay, so here we go. So look at the statement here. The mean age of the students enrolled in evening classes is less than 28 years. So the mean, that's talking about mu, of students is less than 28 years. So that says mu is less than 28. That has to be the alternative hypothesis, H1 or HA, because when we write the null, we always write it using equality. So you would say mu equals 28. All right? And then a lot of the time you'll have to identify, was the claim in the null or was the claim in the alternative? So when you read this statement here, this conjecture, saying that the students enrolled, the mean age is less than 28 years, that's the statement represented by the alternative hypothesis. So the claim is here. Okay, let's try another one. The mean distance from home to the nearest fire station is 4.3 miles. So mean, mu, is means equals 4.3. That would have to be our null hypothesis. Remember, we use equality for the null. So how would you set up an alternative? Well, it's just going to basically be the opposite of what the null is. And in this case, they didn't indicate that we're interested in greater or less than. So you just write mu is not equal to 4.3. And read the conjecture again. Is that statement, is the claim in the null or in the alternative? The mean distance from home to the nearest fire station is 4.3 miles. This time the claim is in the null. One more. The mean weight of college football players is no more than 225 pounds. No more means less than, right? Less than or equal to, but we don't put equality with the alternative. We only put it with the null. So mu is less than 225. That's my alternative. Let me use an A this time just to spice it up. And then the null, mu equals 225. Where was the claim? In the alternative. Good. So notice the null hypothesis is always stated using equality, an equal sign. And in a study, it's typically assumed that the parameter is equal to a specific value, like we saw here. Okay? So after this first step is done, after this hypothesis has been made, then a study is designed and an appropriate statistical test is chosen. We will learn various statistical tests and when to apply each one. That's basically what we're going to do the rest of the semester. A statistical test uses data obtained from a sample to make a decision about whether the null hypothesis should be rejected or not. The test is used to determine whether the sample evidence is different enough to suggest that the true parameter value differs from the assumed value. Okay, so here's basically what happens. Say I were to make a conjecture that the mean age of students taking my class is 22 years old. Okay, I could take a sample of 10 students from my class. I claimed, let me write this out for you guys. So I claim that the mean age of students is 22, okay? And then I find a sample mean, and it's 26. Does that mean that I'm wrong? Maybe, maybe not, right? 26 isn't 22, but it's not so far from it. So when we use a hypothesis test, we're going to compare two quantities to see if that difference is enough to say, this was wrong, or maybe we just leave it alone and say we don't know. That's basically what we're going to be doing here. So the numerical value obtained from a statistical test is called the test value. And the way a test value is computed depends on the test that's being used. So we're going to have like a z-test, a t-test, all sorts of tests. Does the sample evidence support the claim? So to decide, we compare the test value to the hypothesized population value. So like I said earlier, I got my sample mean at 26. We said we hypothesized it was 22. So we're going to compare them. To help you visualize the decision process, I want you guys to look at the following examples. So here's the claim. The average is 100. Average whatever, okay? We're not making it very specific. So we're claiming the average is 100. You would agree with that if you found a sample and the sample means average came out close to 100, right? If it was a little less than 100, okay, whatever. Maybe the sample isn't perfectly representative. If it's a little more than 100, sure. The only time you would say I disagree with the claim is if you get a sample mean that's much smaller than 100 or much larger than 100, right? Then you would say, no. But we all give ourselves some wiggle room to say, there's sampling error, so it doesn't have to match 100 spot on. I'm still going to agree with the claim if we're in this realm here. And we'll talk about exactly how to find these values, these cutoff points. That's what we're going to do when we conduct a hypothesis test, okay? But let's just keep speaking more generally so you guys can get the idea of what's going on. So say for the next example, the claim is that the average is not 100. Okay, so the only difference now is if the average is not 100, that claim is in the alternative instead of the null. And the null is still that the mu is equal to 100. So where would you agree with the claim that the average is not 100? You would agree if it was much larger than 100 or much smaller than 100, right? That's where you would agree with the claim. You would disagree with the claim if you got an average that was close to 100, a little bit below or a little bit above. So notice you agree and disagree in opposite portions, right, of the graph for 1 and 2, even though the null and alternative hypotheses were exactly the same. The claim was somewhere different. So whether you agree or disagree with the claim changes. All right, let's look at another one. Claim, the average is at least 100. So at least means greater than or equal to. Remember, we don't put the or equal to on the alternative. So mu is greater than 100. That's the claim. The null you always write with an equal sign. So where would you agree with the claim? Well, obviously, for values that are larger than 100, and even if it's a little bit below, you're like, you know what? That's okay. Sampling error. Hey, it happens. But you would disagree with the claim if you got a value, if your sample mean came out much smaller than 100. Then you'd say, no way, no how. Mu is not greater than 100. Okay, here's another. The average is at most 100. At most is less than or equal to, so I'm just going to write mu is less than 100. That's the claim. The null is going to be mu equals 100. So where would you agree? Where would you disagree? Mu less than 100, and you're going to give yourself some wiggle room, right, for sampling error. If we get a sample mean anywhere in here, we're going to say, yeah, I think mu is less than 100. Maybe my sample has a mean just a smidge over 100. It's okay. But if you get this mean that's much larger than 100, then no, you're going to disagree with the claim. Okay. A couple more. Claim. The average is less than 100. That's actually exactly the same as the one we just did here. Average is less than 100 ends up being mu less than 100. That's the claim. Null is the same. So less than, 100 should be here. What happened? I think it didn't paste properly. Excuse me. Let me get rid of this extra little 100. And this guy, this belongs to the graph up above. It's okay. All right. We'll just fill this in. Okay. So remember, we give ourselves a little bit of wiggle room. Mu can be less than 100 or maybe a wee bit over. You would agree this way. And then you would disagree if you land over here somewhere. Okay, last one. The average is more than 100. So that would be the alternative. Mu is more than 100. There's the claim. And then the null is going to be mu equals 100. So you would agree with the claim if you got obviously a mean more than 100 or even a little bit lower, right? You say, it's okay. I'm going to agree here and disagree if we land over here, well below 100. Okay. From this point, a decision is made to either reject or not reject the null hypothesis by comparing the test value to the proposed population value. If the difference between the two values is significant, then we reject the null hypothesis. If the difference is not significant, then we fail to reject the null hypothesis. Those are the only two decisions that you can make when hypothesis testing. So notice you can either reject the null or fail to reject the null. You never accept the null, Okay, you can either reject it or fail to reject it. Now, there's 4 possible outcomes, all right, when you're conducting a hypothesis test. So let's look at each of these. I've organized them into a little chart. So say the null hypothesis is true, say it's true, and you reject it. Did you make the right decision? It's true and you rejected it. No, that's an error. Uh-oh. We call this a type 1 error. Okay. All right. However, if the null is true and the decision is fail to reject or do not reject, then that's the correct decision. Yes? Okay. Yay. Of course, you'll never know. You'll never know unless you get the parameter value. So we're just looking at what's possible. Say the null hypothesis is false and you reject it. And you reject it. So we're over here. The null is false, you reject it. Yay, good job, right? That's the correct decision. And then last scenario is that the null is false and you don't reject it. It was false and you didn't reject it. Oh my goodness, another error. Error, type 2. We call that one type 2. Okay. So what's the relationship between type 1 and type 2 errors? Well, for a fixed sample size, the smaller we specify the significance level, we'll talk about what that is, alpha, the larger will be the probability beta of not rejecting a false null hypothesis. So basically, as one goes up, the other goes down. Okay. Type 1 error and type 2 errors are kind of classified a little differently. So a type 1 error is usually considered to be more severe than a type 2 error. So what we do is we restrict the probability of a type 1 error to be very low. In a given test, decreasing the probability of a type 1 error, though, increases the probability of a type 2 error and vice versa. So they're inversely related. But because, we're more afraid of having type 1 error occur, that's the one that we restrict and keep low. Calculating, and we set that probability. We say we don't want it to be any more than this number. Now, calculating the probability of a type 2 error is difficult. If you're very interested, you can read more about it, type 2 errors and the power of a test, but that's beyond what we're going to need to cover in this class. Okay? So to kind of help drive this point home, a useful analogy for hypothesis testing and the errors is a jury trial. There's a spicy jury trial this summer, so maybe you guys are tuned into that. So think of the null hypothesis as being the defendant is innocent, and the alternative hypothesis is the defendant is not innocent. There are 4 outcomes. So let's write it out. So H naught, the null, is that the defendant is innocent. And then the alternative is that the defendant is not innocent. And this is basically the same chart that we had earlier, but now we're kind of putting a little bit more of a situation, some context here. So if H naught is true, then that means the defendant is innocent. And if H naught is false, that means they're not innocent. If you reject H naught, then that means you're going to convict the defendant. And if you do not reject H naught, then they are acquitted. Pretend you're on the jury. Okay, so say we are in this case here where the defendant is innocent, but you convict them. Is that good? No, that's type 1 error. Okay, basically you're sending an innocent person to jail, or you're penalizing them in some way. What if we're over here? The defendant is not innocent and you convict them. Good job, right? Correct decision. All right, what about over here? The defendant's innocent and you decide to acquit. They are acquitted. That's correct. Good job. What if they are not innocent and the jury does not convict. They acquit. That's an error. That's type 2 error. Okay? So basically, we want to limit type 1 error when we conduct hypothesis tests. We want to limit how many innocent people we convict. And at doing so, you know, a little bit more type 2 error has to occur. But type 1 error is considered more severe. Now, keep this in mind too, because this is just like with hypothesis testing. The decision of the jury does not prove absolutely that the defendant did or did not commit a crime, right? Just because the jury says something, that's not definitive proof. A verdict is based on the strength of the available evidence. So all they can do is hear testimony, look at evidence that's presented, and based on the strength of that, they make a decision. And the same idea is true in hypothesis testing. We cannot prove a statement absolutely. The only way to do that would be to conduct a census and actually get the true parameter value. It's not going to happen. But we make a decision based on the significance of the available data. And the only way, like I said, to prove the true value of a parameter is to calculate it using the entire population, which is usually impractical, if not impossible, okay? So how is significance determined? Terms to know. The level of significance is the maximum probability of committing a type 1 error, and that is symbolized by alpha. So you will see oftentimes in some of your homework exercises, alpha is specified. It's given to you for a hypothesis test. The critical value separates the critical and non-critical regions. And we often denote the critical value, we love abbreviating over here, by CV. Yes. The critical or rejection region is the range of values of the test value that indicates that there is a significant difference between the test value and the proposed population value, and that H0, your null hypothesis, should be rejected. The non-critical or non-rejection region is the range of values of the test value that indicates the difference between the test value and the proposed population value was simply due to chance sampling, and that H0 should not be rejected. Okay? I know it's a lot. The cool thing is we're just going to learn different tests to apply for different scenarios. So you only need to learn this main idea about what hypothesis testing is once, and then we're just going to keep repeating and building on it the rest of the course. So this is for sure the toughest part. Okay, hang in there. Now, we're going to talk about one-tailed and two-tailed tests. And you've already seen examples when we were setting up the null and alternative hypotheses and some of the other examples. A one-tailed test indicates that H0, the null, should be rejected when the test value is in the critical region on one side of the mean. So a one-tailed test occurs when the alternative involves less than or greater than. We're only interested in one side of the mean. A one-tailed test is either right-tailed or left-tailed, depending on the direction of the inequality in the alternative hypothesis. Okay. Alternative. Cool. So let's look at some examples here. And these are all one-tailed tests, okay, that we're going to look at. I did change the alpha level if you have the original printout of the notes, so just update it. So first example, the mean age of the students enrolled in evening classes at Harvard University is less than 28 years. Using alpha equals 0.05, label the critical value, critical and non-critical regions for the hypothesis. And really, this alternative should be written below the null. Mu is less than 28, okay? So here they're saying at alpha equals 0.05, okay? This is a left-tailed test. Why do I say that? Because look at my alternative hypothesis. It states that mu is less than 28. Less than means we have a left-tailed test. So here's what it would look like, and here's how we can find the critical and non-critical regions. Whatever alpha is, 0.05, since this is a left-tailed test, that's the probability or the proportion of area for our normal curve that needs to be in the left tail only. Okay, so since alpha is set at 0.05, this area here needs to equal 0.05. All right. That region to the left that contains that 0.05 area, this is right here the critical region. The other portion, all of this, is the non-critical region. Okay, and the critical value is the z value that separates those two regions. How can you figure it out? Well, remember when we were setting up our confidence intervals in the last chapter, I gave you some of the values for z sub alpha over 2. And I told you you didn't have to memorize them because they were in StatCrunch, but some of them come up a lot. Okay, so for that one, maybe you remember, but that critical value corresponds with plus or minus 1.65. But since it's a left-tailed test, we're going to just use the negative 1.65 this time. So basically what that tells me is here's 0, right? The mean for my standard normal. And right here, the z value that separates the critical and non-critical regions is negative 1.65. So 1.65 standard deviations to the left of the mean. That's our critical value. Later, I'm going to show you how we find the test value. If the test value falls here, falls in the critical or rejection region, you reject the null. If the test value falls in here, it's non-critical, you fail to reject the null. That's it. This negative 1.65, if you want to memorize, or, we're going to be using StatCrunch, so you don't have to. But if you probably put some of those z sub alpha over 2s on a note card, it might be helpful. Let's look at another. The mean weight of college football players is more than 225 pounds. Oh, okay. Using alpha equals 0.005, label the critical value, critical, and non-critical regions for the test. So the null and alternative are already there. Let me move the alternative down here. Mu is greater than 225. In this case, since the alternative involves greater than, right, mu is greater than some number, this is a right-tailed test. So what does that tell me? That alpha, that 0.005, needs to be in the right tail. That's the probability or the proportion of area under the normal curve in the right tail. So here, this is all, let me put my 0 here. This is all going to be 0.005. Okay, that's my alpha. So this region in here, that's my critical region. And then all of this is the non-critical region. Do you know what critical value over here, this is the critical value, that separates the critical and non-critical regions? Which critical value corresponds with alpha 0.005? Well, since this is a right-tailed test, if you think back when we did the confidence intervals are always going to be two-tailed. We'll get into that in a minute. But just doubling that, that would be 0.01. And remember the z sub alpha over 2s, it would be plus or minus 2.58. So this is 2.58. If you're freaking out, please don't. So remember, we can go into StatCrunch and you can just open up your normal calculator, normal distribution calculator, and then just type in, if you don't memorize the 2.58 or put it on a note card, type in, you go backwards, right? That the probability is greater than, the probability is going to be 0.005 for greater than some number, and it will give you this critical value. It's just some of these come up so much, I have them memorized at this point, and it might help you too. All right, those are one-tailed tests. Now, a two-tailed test indicates that H naught, the null, should be rejected when the test value is in either of the two critical regions. So you'll have two critical regions for these. Let's look at an example. The mean distance from home to the nearest fire station is 4.3 miles. I want the null down here. Using alpha equals 0.05, label the critical values. This time we have more than one, critical and non-critical regions. So what makes it a two-tailed test is that the alternative has does not equal to in it. Then it's two-tailed. So if it's greater than or less than, it's one-tailed. If it's not equal to, it's two-tailed. It's really that simple. We're going to use alpha equals 0.05. Okay. So what does that mean? You actually have to split that between each of the tails. So cut 0.05 in half. You would have 0.025 in this tail and 0.025 in this tail. That's the difference for a two-tailed versus one-tailed test. The alpha gets split between the two tails. Each of these is a critical region. This is a, let me move the arrow into the region. That's critical region number 1. And then this is another critical region. So if your test value falls in either of those regions, you would reject the null. The middle is the non-critical region. And what are the critical values? Well, one of them's over here, and one of them's over here. And I don't know if you remember your z sub alpha over 2, but it's plus or minus 1.96. This time we have both of them. This is positive 1.96, and this is the negative 1.96. Okay? So again, those are the most popular ones, 1.96, 2.58, and 1.65. So that's the reason I have them memorized. I don't have any others memorized. There's only 3, so don't stress. Okay. From here, now we're actually going to do real hypothesis tests. I think it's a good time for you guys to take a little break, have a snack, okay, and then come back. We'll finish this up. I don't want you to get all worn out right now. So stay tuned. We got more to come. Don't forget to give the video a thumbs up and subscribe if you haven't already. See you guys soon.